Okay, now that we have seen in a previous video the structure and functional activities of myoglobin, let's expand this into looking at hemoglobin. Now, if we look at the kinetics of oxygen binding, the best way to look at this for hemoglobin is if we examine it in comparison with myoglobin. So what we're going to measure here is oxygen binding, which is also called oxygen saturation. So we're going to measure the amount of oxygen bound on the y-axis, and the substrate that we are going to measure is the partial pressure of oxygen on the x-axis. And of course, being a gas, this will be measured in millimeters of mercury. Now, if we examine the binding characteristics of myoglobin, we would see that there is a very high affinity binding property. So myoglobin equals a very high association constant, which also equals a very low dissociation constant. So that means the reaction of oxygen with myoglobin is going to favor oxygen myoglobin complex formation. So what that looks like is a saturation curve. So this is myoglobin. Now the myoglobin has very high affinity binding because, as you can see, the slope of this line is very steep, which means that the change in oxygen binding bound over the change in partial oxygen pressure is a very high number. This defines the high affinity of myoglobin because it doesn't take much oxygen to bind very quickly, rapidly, and to saturation for the myoglobin. Now, if we look at hemoglobin on this same curve, what we would see is this. This is hemoglobin. With hemoglobin binding, notice that we have transitioned from a hyperbolic curve into a sigmoidal curve. What the sigmoidal curve indicates is cooperativity. This also equals multiple binding affinities. So whereas myoglobin has one affinity for oxygen, hemoglobin has multiple binding affinities. It is bound in a manner that is called cooperative. What this means is that we have a multi-subunit structure. Myoglobin, of course, recall, is a single polypeptide. Hemoglobin now consists of 4 individual polypeptides that are bound together. Recall, this is called quaternary structure. We have 4 monomeric proteins, all in their tertiary conformations, that have come together to form a heterotetrameric complex. That's quaternary structure. In this case, we have a heterodimers form, which are 2 alpha globin proteins and 2 beta globin proteins. Each one of these subunits has heme with iron bound. So there is 1 heme unit per subunit for a total of 4 heme iron complexes. Now, what this means in terms of binding is cooperativity in the sense that one subunit will bind oxygen, and then that will induce a change in the quaternary structure so that the next subunit that binds oxygen binds it with higher affinity. And that can be seen on this graph. If we look at low oxygen concentrations and we look at the slope of the binding kinetics, we see that low oxygen pressures indicates a very small amount of oxygen binding. This could be equivalent to oxygen binding to the first subunit of hemoglobin. Now notice that if all four subunits bound oxygen with the same affinity, we would have a very shallow slope on our line, but it would be linear. What we see now is that with higher oxygen pressures, we see a change in the slope. This means that the second oxygen binding to the second subunit is of higher affinity. At higher oxygen pressures, we would see the next slope where the oxygen is binding to the third subunit at even higher affinities, higher slope. And then finally, if we look at our binding of oxygen to the fourth subunit, we see that it has even higher affinities. So what this indicates is that the first subunit has a specific KD measurement. The second subunit has a higher KD than the first. The third subunit has an even higher KD than the second. And finally, the fourth subunit has the highest binding affinity of all of the subunits. So the binding of oxygen to the first subunit induces higher affinity as we progress. Higher affinity. This is the definition of cooperativity, that one subunit is cooperating with the second one to increase its affinity. This is termed positive cooperativity. Now, why is this important? Well, the importance of this is in oxygen release into the tissues. So let's regraph this. Oxygen bound versus partial pressure of oxygen, and let's examine this from a different perspective. Here is our myoglobin. Here is our hemoglobin. Now, let us consider the partial pressures of tissues themselves. If we look at lung tissue, we would see that lung tissue is going to have a very high partial pressure of oxygen. This makes sense because this is the first encounter of oxygen inside the body. So its highest pressure in the body will be in the lungs. Notice the amount of oxygen bound at these pressures. There's so much oxygen here that we can saturate both myoglobin and hemoglobin. This is important because hemoglobin is the transport protein in red blood cells for oxygen. So in the lungs, we want to make sure that we have enough oxygen to fully saturate the hemoglobin. Now let's consider the tissues. let's say this is the partial pressure of the tissues in this range. Now in this range, it makes sense that the tissues will be at lower oxygen pressure, lower oxygen amount than lungs, because tissues are using the oxygen, so it should be depleted from the lungs. Look at the saturation level of hemoglobin. At this midpoint range here, we have this much oxygen bound. Notice myoglobin. What this indicates is that myoglobin has a higher affinity for oxygen than hemoglobin does. And in the tissues, the oxygen will leave the hemoglobin and transfer to the higher binding affinity of myoglobin. So by having this association difference, this binding affinity difference, we can ensure that the hemoglobin is able to release the oxygen in a directional manner to binding to myoglobin in tissues where it is needed. Now, structurally and functionally, how does this cooperativity work? The way I like to think about this is looking at this on the side like we did with myoglobin. Here's our heme structure on its side, 90 degrees. Recall that this is bound to the histidine amino acid of the polypeptide chain. And now when oxygen binds, the oxygen binding to the iron is going to pull this structure out in this direction. The reason it's going to do that is because recall that the nitrogens on the parole ring that are coordinating the binding to iron are going to be in a repulsive mode with the oxygen because they're both electronegative. So the oxygen binding will cause a repulsion of these electrons between the oxygen and the nitrogens, and it will pull the iron actually out of the ring. So what does that look like? We can draw this here. The iron is still bound to the histidine, but now everything is pulled out in this direction. What this essentially does is it causes a conformational change in the polypeptide that this heme is bound to. So oxygen binding to the first subunit of hemoglobin induces this conformational change in one of the subunits, and then this is transmitted to an adjacent subunit because it's bound to it. It's physically bound. So the binding of oxygen is going to increase the affinity because of this conformational change. And because this is a positive cooperation between these, each subsequent binding of oxygen to each of the subunits will induce a conformational change on the next subunit, which will further increase the affinity. The way the textbooks like to draw this is going from what's called a tense to relaxed state. So tense is the unbound form of hemoglobin. Relaxed is with 4 oxygens bound. Now the way I like to remember this is that tense, think of a wound spring. There's lots of energy in a wound spring. So every time an oxygen binds in this reaction, it causes a relaxation of the spring. Eventually, when 4 oxygens are bound, the spring, which would be the quaternary structure of hemoglobin is now in a fully relaxed state. So regarding hemoglobin, the next principle we need to look at is what is called the Bohr effect. Now what the Bohr effect does is it increases the release of oxygen to tissues. Now we just saw that the binding properties of oxygen for hemoglobin are such that the binding affinity to hemoglobin is lower than myoglobin in the tissues, which would allow a directional movement of oxygen from the lower affinity hemoglobin to the higher affinity myoglobin. But to ensure the binding of the release of oxygen and binding of myoglobin, we have another principle called the Bohr effect that helps facilitate this. The Bohr effect is a pH effect. So what we are going to do here is change the pH of the local environment around the hemoglobin molecule to affect its binding properties to oxygen. So how do we do that? Well, once again, let's look at our O2 saturation curve versus our partial pressure of oxygen. And let's draw our binding curve for hemoglobin. Now let's say we do this binding measurement of oxygen to hemoglobin at pH 7.6. So at 7.6, this would be the binding curve of oxygen relative to the oxygen concentration in the environment. Now let's change the pH to 7.2. Let's make it more acidic. What we see, essentially, is a movement to the right. This indicates that the affinity of oxygen for hemoglobin has decreased. So this is a decrease of the association constant and an increase in the KD. And this is all due to a decrease in the pH, the acidification. Now what this principle allows by changing the pH is that if we are in the tissues, let's say that this is the tissue pressure, our partial pressure of oxygen in the tissue, let's say, is in this range. Look at our midpoint. At the higher pH, we would release only this much oxygen from the saturation point to this point. The remainder would still be bound. But if we drop the pH, what we now have is an increase in the release of oxygen. The amount of oxygen bound to hemoglobin decreases, and this excess oxygen is now transferred into the tissues. This is the Bohr effect. So how does this work? Well, recall that we have a gas exchange. O2 is being transferred into the body, but we have another gas that's being transferred out, and that's CO2. The CO2 is from what's called metabolic respiration. Metabolic respiration is simply using oxygen as our final electron acceptor, which we'll get into in oxidative phosphorylation, in order to generate energy. The byproduct of the oxidation of our fuels is CO2. And so CO2 is a waste product. Now the way we get rid of CO2 is CO2 diffuses out of the tissues and into red blood cells. In red blood cells, the CO2 will be combined with water using the enzyme carbonic anhydrase. Carbonic anhydrase will take CO2 and water and combine them to form a proton plus a bicarbonate ion. Recall that CO2 is a gas. So in order to dissolve this gas into a liquid, we have to use this reaction to convert it into bicarb and a proton. This reaction, of course, because of the increase in proton concentration, is going to decrease the pH. So as tissues are releasing CO2, they're indicating that they need more oxygen. So the CO2 is converted to bicarb, the proton decreases the pH, and we have a decrease in the localized pH in this environment, which leads to the Bohr effect, which is an increase in oxygen release. Now structurally, what this increase in proton concentration is doing is the increase in this concentration is stabilizing. You could also say promoting the tense state of the hemoglobin quaternary structure. Now the one final aspect of oxygen binding to hemoglobin is looking at the effects of high altitude binding. Now this is appropriate for those of us that are living here in New Mexico, since we're at a mile high in altitude. And this here, we are going to be examining the effects of a small molecule called 2,3-bis-phosphoglycerate. The structure of this molecule, of course, will have a glycerol backbone from glycerate. 8 ATE indicates that this is a carboxylic acid containing structure. We have 2,3-bis-phospho, which means there are 2 phosphates on this structure. This is the number 1, 2, 3 carbons. So we are going to have phosphate residues on the 2 and 3 carbons. This is 2,3-bis-phosphoglycerate. This is a side reaction from glycolysis in red blood cells. So we are going to be examining this reaction when we talk about glycolysis. But for now, just recall this structure of 2,3-bisphosphoglycerate, also abbreviated 2,3-BPG. Now this small molecule is also going to affect oxygen binding to hemoglobin. So let's look at our binding curve again. Here is our binding of hemoglobin, oxygen to hemoglobin. And let's say this is our binding curve that we would measure at sea level. We have a specific curve. Now, if we do the same reaction and measure this in an individual that has been acclimated to high elevation, we would find the curve being like this. This would be high elevation. Notice again, in a similar manner as the Bohr effect, that the binding curve for hemoglobin for oxygen is shifted to the right. It doesn't take much to do this reaction. Let's say that at sea level, the 2,3 BPG concentration is equal to approximately 5 millimolar in red blood cells. At high elevation, this concentration is going to be increased to, say, 8 millimolar. Now again, notice what this does if we look at the effect in tissues. So again, if this is our oxygen pressure availability range in tissues, notice what we've done. If we look at our midpoint reaction here, this is the amount of oxygen released with a smaller amount of BPG. If we add BPG at a higher concentration, we see that more oxygen is released. So the net effect of 2,3 BPG is to increase the oxygen release at higher elevations. This makes sense because the partial pressure of oxygen is lower at high elevation. So this is decreased partial pressure of oxygen. Basically, the amount we breathe is less at higher elevation. So our red blood cells will increase the amount of this compound, which will shift the curve to the right and aid our tissues in acquiring oxygen. This is why, if you have friends that are at sea level and they come to visit us in New Mexico, if you take a hike in the mountains, they will become more winded, breathing faster to get more oxygen than we do, because they have a lower level of 2,3 BPG, and therefore they release a certain amount of oxygen. At our lower oxygen levels, at high elevations, a little more oxygen will be good for our tissues. And so we're adapted to this with the higher 2,3 BPG levels to release that little bit of extra oxygen, and that gives our tissues a distinct metabolic advantage over individuals from sea level.